All right, let's use this logistical growth problem to solve. So here they give us this differential equation. We can see it's logistical because it's not just directly proportional to P. We also have this information over here which tells us it's going to be one of those logistical ones where the initial population is 100. They want us to find, use this to find the population size where at a time of 40 and a time of 80. Well, there's some information over here you got to be able to pick out. This is our little k value right here. That's our growth rate. This right here, that's our capital K, that's our carrying capacity for this problem. So what we want to do is start with that logistical growth equation, which says population is going to be equal to our carrying capacity over 1 plus A to the times E to the negative little kt. So we know in this one that our carrying capacity that we're filling in, that's our 1,000. Here we got 1 plus, we're going to need that A value. We know our K is negative 0.08 here. T, now we just need A. What is A again? A is that population, or it's the constant where the population is 0. If you can't remember the equation for this one, just think it's if you take this logistical equation, it's what this is when population is 0. So what would we get if we plugged 0 in this? Well, that's going to simplify it a little bit because it doesn't matter what this K is at a time of 0. All this, anything to the 0 power is going to be 1. So now we got our carrying capacity over 1 plus just A because E to the 0 power is 1. Well, let's solve this. Let's multiply this part to the other side. If we do that, we got 1 plus A times P of 0 equals our carrying capacity. Let's divide by P of 0. So now we got our carrying capacity over initial population. If you minus 1 from this now, that's our carrying capacity over P of 0 minus 1. And now if you just make this into a common term here, we'd have our carrying capacity over P of 0 minus P of 0 over P of 0. And if you join that together into one thing, then we get that A that we had on the previous slide where it's K minus our initial population over our initial population. So that's what you want to be using for A when you want to find your A value. So going back to this problem, what's our A going to be? It's going to be our carrying capacity minus P of 0 over P of 0, which our carrying capacity is 1,000. Our initial population, that's what we got here, is 100 over 100. That's 900 over 100, which simplifies to 9. And so in our equation here, this would be 9. All right, so now if you want to find what's P, the population at a time of 40, you're just plugging 40 in for our time here. And then this becomes calculator now to find that out. I've already entered this in here and hit equals, and you can see it comes out to be about 731.604. What is this in? They don't give us what the time is in, but that would be the amount of time there. The other one they wanted us to find here, what is P at 80? So that would be this same equation now, just we're entering in 80 instead of 40 here and seeing what that would be. Easy way to do that on the calculator, if you've already entered something similar, if you hit second, enter, it'll put the last entry in there, and then we can just edit this here. Let's go back in the equation here and change this from 40 here to 80. and hit enter, and we should get this one. So this one would be about 985 0.266. And again, whatever the amount of time, whether this is in years, hours, I'm not sure because they didn't tell us in the problem. All right, the final thing they wanted us to find in this problem is at what time does the population reach 900? Well, we're going to still use our same equation here that we came up with. So we're going to still start with this 1,000 over 1 plus 9e to the negative 0.08t. None of that has changed. What we want to do now, though, is if we want to figure out when this is 900, we're putting that in for our population here, and we got to solve now for the time. So we're solving this backwards now. What do we get if we solve this out? Our goal is to solve for t here. Well, it's not going to do us much good if we got this stuff with the denominator. So let's multiply our denominator to the other side. So now we got 1 plus 9 e to the negative 0.08t times 900 equals 1,000. Let's divide by our 900. That'll help us simplify here. So now we got this equals this would simplify down. We could cross some of those zeros out to just 10 over 9. Now we could get rid of our 1 here. Let's minus 1. So now we got 9e to this equals, if we get a common denominator here, this would be like 9 over 9. So we're going to get 1/9. All right, now let's divide by 9. Or that's the same as multiplying by the reciprocal of 1/9. So that cancels out. So now we got e to the negative 0.08t equals 1/9 times 1/9 would be 1 over 81. All right, how do we solve from here? You can't do any more algebra solving at this point. Now comes that part where you learned about logs. That we want to natural log both sides here. So we want to natural log this side and natural log this side. And that helps us because natural log of e cancels out or equals 1. So now we're down to this. And then finally, to solve for t now, we should be able to divide. So if we do natural log of 1 over 81 divided by negative 0.08, we should get our answer. So type that one in the calculator, and you should see that it comes out to be approximately 54.9, whatever this time is going to be. That's how long it would take the population to get to 900. All right. Some other stuff we should know with this population stuff is when you have logistical growth, you're going to see these curves like we've seen in previous videos when drawing out the solutions, that we have this exponential growth here, and then at some point we stop exponential growth and it tails off towards the carrying capacity. When do we hit that point where it changes from exponential growth to changing towards the carrying capacity? Well, that's where the inflection point would be. So this point right here would be the inflection point, because you're changing from concave up to concave down. And it changes to concave down when you start approaching that carrying capacity. So that inflection point, that's the point of maximum growth. So in these problems, if they ever ask you what is the point of maximum growth, it's the inflection point. And that point in logistical growth always occurs halfway or half of the carrying capacity. So whatever your carrying capacity is, here they're using C before you're using capital K. It's the Y value of this is always going to be half the carrying capacity. So whatever half the carrying capacity would be, that's your y value of that point. The x value, you could then plug that in and solve for it, but it does come out to be the natural log of whatever this a value is here, uh, over, all divided by b, which that in our problem before, if you wanted to write the same point using the variables we were using before, it would be half our carrying capacity over 2 would be our y value. This would be the natural log of capital A, because that's what we had here. And then we were using little k for this. So this would be little k. So that would be what that would end up being at. The big thing you want to remember with this is that inflection point is always going to end up being half the carrying capacity for the y value. And then you should be able to, if needed, solve for that x value from there. All right, let's look at one more example here. In the 1930s, a biologist, Gauss, conducted an experiment with protozoan paramecium and used the logistical growth equation to model his data. The table gives his daily count of the population of protozoa. He estimated the initial relative growth rate to be about 0.7944 and the carrying capacity to be 64 of these paramecium. So here's his observed data here. This is in days, 1, 2, 3, 4, 5 days. So every day he counted. Down here is the number observed. So there was 2, then 3, 22, 16, 39, and so on. You can see the numbers here all the way across. So what we are looking at then would be to find the exponential and logistical models for Gauss's data, and then compare the predicted values with the observed values and comment on which one fits better. So we got that little k. We also have the initial population being 2. So if we were using exponential growth, that's our PERT equation here. So it would be population would equal our P, or our initial population, times E to the RT, where this is the amount after the amount of time, where R is the rate, or in this case, it looks like we're using little k for this, same thing. So let's fill in what we know. Initial population would be 2. We'd have E to the little k, which is 0.7944 T, and that would equal A, or in this case, looks like we've been using P as a function of time, so P as a function of time here would be this. So that would be our exponential growth equation. If we want our logistical one, logistical growth, now we're using our other equation we had here. So our population is going to be our carrying capacity over 1 plus A e to the negative kt, where A again is equal to our carrying capacity minus our initial population over our initial population. Let's find that A value first here. So on this one, we know our, from before they told us what the carrying capacity was, which was 64. So we know here that case is 64. We get 64 minus our initial population is 2 over 2. So we get 62 over 2, or 31. So that's our A value. So now let's fill in the rest of this population equation. It would be 64 over 1 plus 31 e to the negative. We have our k value, 0.7944 t. So that would be our logistical growth equation. So if you were to graph out these two, along with the data points, this one over here, this black one, is showing our exponential growth if we were just allowed to grow forever. This red one is the graph of our other equation, our logistical one, this one. So again, it starts the same, and then somewhere here it's breaking off now and approaching our carrying capacity, which we said was at 64 here. So you can see approaching that carrying capacity. Which one fits better? Well, you can see from the blue points here, the data points, which were the observed ones up here. That's all these blue data points. Initially, maybe the exponential one looks okay. Probably through about day 4 here. At day 4, I think we kind of change. Everything's relatively the same here up until that point. We've got the logistical models all the same here. Here they're all very close. The observed one here, a little more than both models should predict on that one, but it kind of levels off here. All these are fairly close. And again, all these are fairly close. But now you can see at day 5, the exponential model predicts something way more than the logistical one. And that is almost double what the observed amount would be. So at day 5, that's where we're changing here. And you can see these numbers would get exponentially bigger. And we're not seeing that with our observed stuff here. They match the logistical model much better. So that's why you can see logistical model does fit when you have population. I would also suspect here that or we could find where that inflection point would happen if our carrying capacity here is 64, then our inflection point would happen at half of that. So if you take 64 over 2, that's going to be at 32. So where 32 is here, which would be somewhere around here, that's where our inflection point would be. That would be the point at which this is the amount of growth is increasing the fastest. And it looks like it would occur here really close to 4 days. Somewhere right around 4 days is when that would be happening. And we could see from up here, yeah, that must be true when we jump from what we had here to what we had here. Looks like that is when the growth was occurring the fastest.